So we're rolling, Christian.
All right.
I wanted to talk a little bit about some larger scope issues. And I wanted to begin with a comparison of two different times, inflection points in mathematical history. So one inflection point begins in let's see, have I got the time right? I think it's the early 1900s when people begin to drop the Euclid's fifth postulate and realize that they can get sensical geometries out of it. So it's about 100 years ago. And what happens is that suddenly there's a zoo of geometries. There are a lot of different geometries, and mathematicians like Klein want to provide some kind of organization for it. So Klein sketches out his Erlangen program, which captures a lot of the geometries, but not all of them. And if memory serves, it doesn't capture Riemannian geometry. But mathematicians like Cartan and Ehresmann revise the Erlangen program via the notion of a connection, which in some sense characterizes the relationship between a topological space called a manifold and its tangent bundle. And this gives a rather complete characterization of different notions of geometries. And there's a similar inflection point, although I have to say that the time frame in which the inflection point happens is different. So it goes, let's see if let me just quickly consult Google on this. Brouwer law of excluded middle. So what years was Brouwer working? Do you know?
I think around that same time or maybe later.
Was it? I thought it was earlier. Let me just double check.
Oh, sorry. Let's see. Kind of around that same time.
Let's see.
Like early 1900s.
Yeah, that's about right. That's about right. Yeah. Okay, good. Yes, you're right. You're right. You're exactly right. So about the same time then, logicians and mathematicians are beginning to look at dropping some of the rules in classical logic. And Brouwer begins, so it's very analogous to what happened with geometry. Brouwer begins by dropping excluded middle. But then subsequent to that, we see a whole host of what are called substructural logics, and culminating in linear logic, which drops the rules of weakening and contraction. It doesn't actually drop them. It just, it puts constraints. It marks them. Yeah. It marks weakening and contraction. and thereby and through this arises this notion of resource conscious logics. All during this time, we also have another development in logic, which is arises from Kripke's possible worlds interpretation of modal logic, and then Milner and Hennessy pick up on this idea and connect it to the process semantics, the process algebraic semantics, where the possible worlds are possible executions of a process. But nothing gives us a uniform picture of logic in the way that the Cartan-Ehresmann connection gives us a view of geometry. And the way I like to think about the work in OSLF is, so operational semantics in logical form, OSLF, is like that. It's sort of a research program to help us wrap our minds around what is logic in the same way that the Erlangen program and its refinements were a way to help us wrap around our minds around what is geometry. Does that make sense?
Yeah.
Cool. So then one of the things that was a big influence on me as a young researcher was a book from Cambridge University Press called Topology via Logic, in which Steve Vickers gives a view of topology, which was, by the way, my first real love in mathematics. I feel like I genuinely fell in love with mathematics when I encountered topology. It was a really different way of looking at the world.
Yeah.
And so then when I saw this idea of topology via logic, where you characterized a topology as an algebraic structure, and that algebraic structure was closely connected to notions of logic, then I really felt like there was an interesting avenue. And then when I saw the unfolding of the consequences of linear logic, that sort of opened up for me this the possibility that we might see an organization of logic, but also that logic might have things to say, not just about topology, but about geometry.
Yeah. Have you seen anything similar to the Erlangen program for logic?
Well, I mean, I think categorical logic tries to do something similar, but it doesn't give a really it doesn't give a very convincing account of how all the parts fit together with respect to the substructural logics, and how modal logic works. So that's one way in which I feel like it doesn't have the sort of same compelling organizing sensibility that the Erlangen program does. But one of the things that I've been, sort of keeping around in my, to work on when I have, a few down moments, is this idea that we might, in the same way that Vickers transports the ideas from logic into topology and vice versa, that we might transport the idea of a connection. So we might come up with a more abstract characterization of a connection from a logical perspective, and get a logical view on geometry. The logical, topology doesn't give you a geometric characterization of space, right? It doesn't preserve angles and it doesn't preserve distances. So it's very, it's like people like to call it rubber sheet geometry or something like that. But yeah, it doesn't concern itself with those kinds of worries and concerns. But if you're anyone who's sitting in a car at a traffic light wondering if there's a different route to take, might have geometric concerns. So I have wondered whether or not there might be a logical view of geometry where angles and distance and their like might be characterized geometrically.
What do you think? I mean, the distinction between topology and geometry, is there a logical analog of that distinction?
Well, one of the things that I've been thinking a lot about is this notion of splitting as a way of locating things. So if you look at Conway's games, in which he generates the not only the real numbers but the surreal numbers and lots of other numbers besides, that can be viewed as a kind of generalization of data kind cuts. And both of them can be seen as a way of splitting a structure, what's to the left and what's to the right. And so when I saw the zipper construction, which locates a subtree inside a context, and so it defines a notion of location by splitting an object into a context in a subtree.
Yeah. I
began to wonder if that might be a notion of location that we could transport via logic.
Yeah.
So that we might be able to we might be able to get something like something like charts over a manifold structure to begin this idea of developing a notion of connection. And one of the interesting things, and this is sort of what connects with the work that you and I've been working on, is that once you have generated a logic over some algebraic structure, you automatically get a topology. So if we associate formulae and their extension, so let's take as our universe the set of terms that are generated by some model of computation, like SKI or lambda or row calculus, whatever it is. So our universe is going to be the set of terms generated by that model of computation. Mm-hmm. And our so in general, to specify a topology, I don't have to specify all the opens. It suffices to specify a basis, or even what's sometimes called a sub-basis. Mm-hmm. I can, as long as the logic that we construct will admit infinitary conjunctions, then we automatically get a basis, not conjunctions, disjunctions. We automatically get a basis for a topology. Because all we need is finite conjunctions and infinitary disjunctions, and a top and a bottom, and we've got our topology.
What are the elements of the basis?
So the elements are the formulae.
Oh, okay.
Or you can think about them either as the formulae, or you can think about them as the extensions. So if you need to think about it in terms of point set topology, right, then it's the extensions of the formulae. But if you think about it in this point-free way, in the topology via logic approach, then you get then it's the formula itself as opposed to its extension. And here by extension I mean the collection of terms that satisfies the formula.
Are you including formulae that are just satisfied by a single term?
Mm-hmm.
So then wouldn't the topology just be like all possible subsets of
The discrete topology?
Yeah.
You can do that, but the nice thing is that you don't have to take all the formulae, right? You can take a generating set of formulae, and then you get different topologies on the terms.
So what would be like an example basis of formulae that we care about?
So for example, you might take, in the case of the row calculus, generating input terms from a particular namespace, for example, right?
Yeah.
And output terms from a particular namespace. So that would be an approach. Again, the point is that lots of them are available, and you use the ones that are going to give you a notion of neighborhood that is useful for what you want to do.
Yeah.
So in particular, the things that seem like reasonable neighborhoods are structurally similar and reachable within a certain number of steps.
Yeah.
Right. And so that's a reasonable generating set for a lot of notions of computation.
Yeah, that's cool.
And now, interestingly for us, our arrow type, this rely guarantee construction, the arrow type formulae pick out contexts. So now you can select contexts, and if you have context and term pairs, then you have locations. So at least in the sense of, the zipper construction. So you can define a notion of chart that is a collection of these arrow formulae, right? So every inhabitant of an arrow formula is going to be a context. And you can lay that over top of your topology. And then you have to have an analog of the differentiability condition. So when we're building up a chart structure, an atlas structure on top of a manifold, when two charts overlap, you need there to be a differentiability condition in the overlap. And that's what makes the thing work in terms of a notion of differentiability, and allows you to essentially what it does is, and I pointed this out in a recent talk about this. The whole thing really pins you down to something very, very close to what you can get from real space, right? So some product of the real number lines is going to give you your grid over your space and give you a notion of location, but that pins down your topology. So specifically, you have this very clear separability conditions. So, right, Hausdorff gives you super clear separability conditions, which are not generally true of models of computation, right? At least with the usual notions of separability. A lot of models of computation, for example, the Scott topology on Scott domains is not even T1, right? So you don't have these kinds of separability conditions.
Sorry, did you say we're thinking of collections of contexts as charts?
Yes, we're going to think of them as charts. That's exactly right. And what I was doing was to kind of go a little bit deeper into the standard notion of an atlas on a manifold, and what that does in terms of the kinds of spaces you can lay locations over, right? So it really pins you down in terms of the kinds of topological spaces you can give a geometry to. It looks very similar to real space. Not like, it's not Euclidean, but it's only a certain range of kinds of things that you can do on top of real space. If that makes any sense.
Yeah. Could you go into a little more detail how we're thinking of contexts as forming some kind of chart?
Yeah, sure. So are you familiar with the zipper construction?
Yeah.
Okay, all right. So the idea is that for those people who might be listening, that if you wanted to locate an element in a tree, you could take the subtree below that element. So starting with that element as the root, finding the subtree, and then take the tree that the context which would get you to that element. So you split the tree into those two pieces. A tree with a hole in it, together with the subtree starting from that element, and that pair locates that element. If you think about it, if you just had the context, you could plug all kinds of subtrees there. So context is not enough. And if you just had the subtree, you could put it into lots of different contexts. So that's not enough to locate, but the pair is enough to locate. Mm-hmm. So now if I have a term, I can consider, which is just a syntax tree, I can consider locating the term in a context,
Mhm.
right? And so now if I have some formula, which is an arrow formula, it's going to denote a set of contexts.
Mhm.
And now I can think about, for a given open, I can think about locating all of those terms in each of those contexts.
And the open being another formula.
Yeah, the open is a formula, exactly. So now we can start to think of sets of arrow formulae over topologies and over a topology imposed upon our universe of terms,
Mhm.
right?
Yeah.
But that's not quite enough, right? And this is what I was trying to get at, which is that the differentiability condition on the overlapping charts, we need to find an analog of that.
Yeah.
Right. And so now this is an idea I've been playing around with. I'm not saying that I have a solution that is like immediately obviously compelling. I think there are lots of different solutions that we can consider, but one that seems natural. So let's think about what is it going to mean for two arrow formulae to overlap, right? So the whole is the thing that's on the left-hand side of the arrow.
Mhm.
It's what you supply. And so when two arrow formulae overlap, it's because the thing that you put in the left-hand side of the arrow is the same, or that they have similar extensions. So there's a conjunction that will fit in that would fit in that region.
Yeah.
Right. So then what you want to do is you want to ensure in the topology that that you've got that the consequent, if you supplied them, that you don't sort of run off the edge, as it were. That the terms that you would get as a consequent are there in the topology. Does that make sense? You understand what I'm saying?
I think so. So if you have a arrow type sigma, arrow tau, and another sigma prime, arrow tau prime, they overlap in sigma intersect sigma prime,
Yes.
and we want to check that the result
Yeah.
is in tau intersect tau prime,
yes. No, not tau intersect, tau union.
tau union tau prime.
You want to make sure that the smallest overlap but the smallest input, widest output. So
Okay.
you can't possibly fail, right? And you need to make sure that that thing is available. Now it will be available since it's a finite disjunction. But you also need to make sure that the charts locate those points, that those points are not outside of your chart. Your chart has to cover those points as well.
Those points being tau union tau prime.
Yeah, exactly. That's
Okay.
exactly right. Yeah. So this is the kind of thing that I think about a lot is trying to make sure that when we're we're solving for OSLF, that we get utility on a lot of different fronts. So one area of utility that I continue to stress is providing type systems that will guarantee that our programs are more robust, without having to do a lot of hand reviews. The other thing is I want to make sure that we have this query capability so that we can use these type systems to find programs or other computational gadgets out of a sea of computational gadgets like GitHub. And then there's this natural movement from this idea of using types to find programs to a notion of types or formulae that locate in the sense of in a geometric sense. And that's really what I've been trying to talk about today, is how if we were to push this analogy, how far could we get? How far could we get a geometry via logic where we're relatively literal? So we look at the refinements of the Erlangen program and say, now that's pretty successful. Virtually all the notions of geometry that have been put forward are captured by this idea. So can we give an abstract characterization that would give us a geometry of computation?
Yeah. Right.
So that's essentially the program, and I feel like keeping our eyes on the prize, in the sense that whatever when we go down the checklist of does our notion of logic do this, does our notion of logic do this, right? That this kind of thing should not be too far down the list in terms of priorities, because it I don't know, it's useful to dream.
Yeah.
Was any thoughts or comments about this approach?
I think it's really cool. This idea of the topology being structured by structural or behavioral similarity sounds very, very useful in terms of being able to actually explore these huge spaces of code. And this connection to manifolds sounds really cool. I don't have a good enough intuition yet. But yeah, it sounds really promising.
Well, we'll have to see. I mean, it may all crash and burn, right? I mean, I just, it's only been in the last little while that I've really begun to absorb the Erlangen program in a way that I can start, seeing whether or not we're, we could make any sort of headway whatsoever. And this particular approach to using the zipper construction may not pan out, but it's, but I, personally, I mean, I just have this strong intuition that there's something deeper, there's something more to this idea of splitting an object into a context and a sub-object than we have yet understood, right? And I think it's a different insight on the same kind of thing that we do in mathematics all the time, right? The first, you define some domain, whether it's a topology or a manifold or a group, any of these kinds of things. And the first thing you do is to say what a sub one of those things is. You know,
Yeah.
what is a component, right? And this idea of thinking about, you know, components in terms of context and sub thing. I don't think we've got to the end of that yet. And there's a close connection between that and power object, right? So there's something there, right? So the object of that is all the sub objects of a thing. And there's something about the way category theory looks at it has utility, but I don't think it quite captures this context splitting idea yet. But maybe that's just because I haven't understood it properly.
Yeah, I mean, from what I've heard, there's a nice categorical characterization of zippers in terms of derivatives.
Oh yeah, for sure. Yeah, yeah, absolutely. The derivative is a very nice notion, but how that notion relates to sub-object classifier, for example, is not clear, at least to me.
Yeah. Yeah, I don't think people have meshed the topics of zippers and these polynomial functors with topos theory very much.
Yeah. Yeah, exactly. So there's go ahead. After you.
Well, yes. Something else I was thinking about was, I mean, the categorical notion of topology, in the distinction between pre-sheaves and sheaves. You can put a topology on a category, picking certain covers of each object, and then require, rather than looking at all pre-sheaves on a category always to assign sets of data, you look at the ones that preserve this local to global piecing together of information. And I've been wondering about that when we take a language and make it into a category. What are the useful topologies that we could put on it? I think that might be really similar to your idea of putting it on the lattice of formulae. I think those might even kind of be the same idea. But you could maybe do it at the source, like in the language as a category.
It would be nice if we do the same.
Yeah.
That would
Yeah.
That would be lovely. Yeah.
Not sure.
Yeah. I mean, you know, it would be incredibly pleasant to be able to use a lot of geometric intuition to reason about programs. Not the least of which is that we have tons and tons of computational apparatus for geometry. Right? I mean, you know, and literally millions of years of evolution in our brains to be able to do geometric processing very, very well. So if we could begin to yield that against programs, I think that would be very, very powerful, very useful.
Yeah, definitely.
So that's another reason to do that. Well, I mean, really, that's all I had for today. I thought it might be fun to just, you know, occasionally just, you know, talk about these wild-eyed ideas.
Yeah.
Do you have any closing comments?
No, I don't think so.
Okay, cool. All right. Well, I'm looking forward to our next conversation about varying the base on the proof sheet construction. That should be
Yeah.
fun.
Yeah, that sounds good.
All right. Well, you have a good day.
All right, you too.
Ciao, ciao.